Hello, welcome dear students. In this video, we will discuss in detail the chemistry of furan. In the previous video, we had an introduction of heterocyclic compounds, and now it is a detailed discussion. Chemistry of furan. Furan is also known as furfuran. This is the molecular formula C4H4O. You can see the structure. Oxygen carries 2 lone pair, and the systematic name of furan we learned, it is oxole. Okay, now we will be discussing preparation and properties of furan. Starting with preparation, we have 3 starting materials. The first one from mucic acid, which is also called galactaric acid. You know galactose, which is an isomer of glucose, which is a hexose. So remember, galactose is the C4 epimer of glucose, which you learn in detail in the stereochemistry of carbohydrates. So this mucic acid, which is also galactaric acid, on dry distillation loses carbon dioxide and water and first form this compound which is called furoic acid. This is furoic acid. Okay, which on further heating loses this carbon dioxide, okay, and form furan. We can understand how this reaction or cyclation has taken place. Look at this. Let me write this mucic acid or galactaric acid like this. See, there are 4 CH-OH groups, okay. So 4 CH-OH, then at the 2 ends you have COOH. It's a dicarboxylic acid. Okay. So what happens? See, dehydration, 2 water molecules is lost. That is this one and this one. Okay. And actually it is not 2, actually it is 3, because 1 more water is lost from here. Then the cyclization takes place. So this becomes double bond here, oxygen here, and there are 2 COH, and here 1 carbon dioxide is lost, that is minus CO2. So you get this one, furoic acid, which on further decarboxylation gives furan. The next one, starting from succinaldehyde, you know succinic acid, we have discussed earlier. That is a 1,4-dicarboxylic acid, and it is the aldehyde analog. So this is 1,4-dicarbaldehyde, 2 aldehyde groups. So this is succinaldehyde, which on heating with P2O5, that is a dehydrating agent, loses 1 molecule of water and form furan. Okay. So that reaction can be understood like this. Look, this is succinaldehyde, which I can, we know this is aldehyde and ketone, you know, they have enol form. So when this enolize, it will be like this. CH double bond, 1 hydrogen will migrate to this oxygen and it become what? It become OH, like this. Here also, CH double bond, CH-OH. So it's very simple now. What happens? It loses water here and it forms furan. Then the third method from furfuran. What is furfuran? It's a common name of, what is the systematic name of this furfuran? It is furan 2. See, when we number heterocyclic rings, we start from the heteroatom. So this is position 2. So what is this? Furan to carbaldehyde. Okay, and it is commonly called furfuran. It on hitting with nickel, Rane nickel, spongy nickel in presence of nickel, or you can also use calcium oxide. Heating at high temperature loses carbon monoxide and forms furan. Okay, so these are 3 methods of preparation of furan. Right. Now on to properties. In the properties, first we discuss structure. Very important. We have 2 angles of discussion. One we discuss in terms of resonance or resonance structure of furan, and then we look into the orbital picture, that is hybridization. So what is the resonance structure of furan? Let's draw it. You should practice this one, drawing it. Okay. There are 2 lone pairs on oxygen. Okay. So we know this is in conjugation, in resonance, not only pi electrons rightly positioned, lone pairs also take part. So this lone pair will get delocalized over here, and this will shift to this carbon. We get the second structure. So what do you get? This is intact. This becomes double bond here. One lone pair is intact, and here comes a positive charge, correct? And this is moving on to this carbon, appear as a lone pair and negative charge. This will continue. Okay. The third structure. You get lone pair positive charge, double bond here. Now double bond comes here, and negative charge is here. Next one, this shifts. The next structure will be double bond here, double bond comes here, positive charge is there, and now it is here. And finally you get the next structure, double bond here, and it is now here, and here there is negative charge and lone pair, and the positive charge is there, lone pair is there. So there are 5 structures. In short, it is that negative charge appear on all the 4 carbons. You can see that, except this negative charge is there on all the carbons. This is the resonance structure. Now comparing with benzene. Benzene is aromatic, it is having high resonance energy. So due to this resonance phenomena, furan is stabilized. The resonance energy is minus 71 kilojoule per mole. We know that it is much less than that of benzene. Benzene is having more resonance stabilization. How do you explain? In benzene, there are equivalent resonance structures, Kekulé isomers, Kekulé forms, identical and equivalent resonance structures. Here, you can see these are not equivalent, and there is charge separation, then the resonance stabilization is less. Now here, when you apply Huckel rule, what is the Huckel number here? It is 4n plus 2 pi electron, that is Huckel rule, where n here is 0. So, not 0, it is 1. N is 1 here. So what do you get? 4 plus 2, that is 6 pi electrons. So, like in benzene, furan is also having 6 aromatic electrons, or aromatic sextet, 6 pi electrons. And remember that is acquired by the involvement of this lone pair. So lone pair on oxygen is utilized in attaining aromaticity. It is delocalized and acquire complete cyclic conjugation. Okay. Now, keep this resonance structure in mind. It may account for very many other properties also. Coming to the next one, hybridization. The hybridization of carbon in furan. See, furan has got 4 carbons and 1 oxygen. Remember that all atoms are having sp2 hybridization. Actually, it is a necessary and sufficient condition for aromaticity. So that's very simple to understand. Let us explain now. So, carbon, we know 1s2, 2s1, 2px1, py1, pz1. That is the excited state configuration, and this is how they mix up for sp2 hybridization. So all 4 carbon atoms here are in sp2. Whereas oxygen, the difference is what? It has 2 more electrons compared to carbon. So here all orbitals are having 1 electron, but in oxygen 1 sp2 will be having 2 electrons, and also the unhybridized orbital also will be having 2 electrons. Okay, so that's the difference. Let us see the orbital picture. How does it come? See, if you consider the sigma skeleton, okay, of this furan, it comes like this. Suppose now here, consider 1 carbon for example. This carbon has got every carbon is in sp2. So what happens? 2 sp2 hybrid orbitals will be utilized by each carbon for forming sigma bond with the neighboring carbon. These are all carbon, right? So 2 sp2 orbitals which contain 1 electron each used for that. Now the third sp2 hybrid orbital is used for what? For overlapping with hydrogen. So that's the case on all 4 carbons. Now what about oxygen? Oxygen also in sp2, I told you. So this is 1 sp2 hybrid orbital, this is another one containing 1 electron each, and the third sp2 hybrid orbital on oxygen has 2 electrons. That is 1 lone pair. Now the unhybridized orbitals on each atoms, carbon as well as oxygen, difference is in carbon there will be 1 electron in the unhybridized orbital. So let us now consider the pi orbitals. Okay, on each carbon there is an unhybridized orbital which will be perpendicular to the hybrid orbital, so it comes like this. On each carbon 1 electron each. But what about oxygen? Remember, oxygen has 2 more electrons than carbon, so 1 electron is here and the other one is in this unhybridized orbital, so it has 2 electrons, whereas the unhybridized orbital on each carbon has only 1 electron. Anyway, what happens is that they will overlap laterally, okay, overlap above as well as below the plane, forming 2 lobes, right? If this is the plane of furan, there will be 1 pi lobe above the plane and 1 below the plane. So the point is, the orbital used by oxygen for forming this pi cloud is the unhybridized orbital containing lone pair, whereas oxygen has another lone pair which is present in the sp2 hybrid orbitals. So remember that. Okay, so that's about hybridization. Now we have reactions. Important reactions of furan. We will discuss some important reactions only. Okay, listen. In the reactions, the most important one is the electrophilic substitution reaction. Similar to benzene, furan, which is aromatic, which has an delocalized pi electron ring, so it is exposed to electrophiles. So it can undergo electrophilic substitution reaction just like benzene. We'll take a few reactions as examples, but then we will discuss some other reactions. Before we go to the electrophilic substitution reaction, how do we compare the reactivity and orientation of furan with benzene? We know benzene. Between furan and benzene, what about the reactivity towards electrophilic substitution reaction? Whether it is more reactive or less reactive. What do you think? Interestingly, it is more reactive. Why you know? Because during the resonance structure we have seen that the lone pair is moving over to the carbon atoms, right? We have seen that in all the 5 structures, negative charge appear on all the carbons, indicating what? Carbon become more electron rich due to this delocalization or resonance phenomena. So, furan is more reactive than benzene towards electrophilic substitution reaction. You understand? Then the second point is regarding orientation. That's very important. Orientation means, see, in benzene, all positions are equivalent. So there is no question of where the electrophile attack, all equivalent. But in monosubstituted benzene, there is a question where the second attack takes place. But here in furan, you have to think about where the electrophile preferably attack. I had told you that numbering is, see, this oxygen is number 1, position 2, position 3. And this is 4 and 5. But when you consider the attack or the orientation, this is position 2. If you take this way, this is also position 2 and position 3. So there are 2 positions because these two are equivalent. These two are equivalent. So there are 2 options. Let us check that. What is the orientation of substitution in furan? Okay. So how you do it? In organic chemistry, the predominance of a product is explained by the stability of the intermediate. That's all. That's the kinetics. Okay. Or that is the energetics as well. So what you do is, you consider both attack. If attack is at position 2, you draw various resonance structures, the intermediates, and see how far it is stabilized. Similarly, you can consider attack at position 3. So position 2, position 3. Let's check. If attack is here, position 2, what happens, Electrophile is attacking here. So plus electrophile. Electrophile, let us show E plus, for example. So it is attacking here. So what you get? You get it like this. The first structure will be when it is attacking position 2. There is one hydrogen here, So that hydrogen is to be replaced later. And electrophile is attaching here actually. What happens is this electron is used for bonding with electrophile. So what happens here? There will be a positive charge, and because this electron is lost by this carbon for the time being. Okay, and avoiding lone pairs now. Now this will be shifting. You have, so this is the intermediate, which is resonance stabilized. Okay, so it becomes double bond here plus here. There are 2 bonds here, and this lone pair now can move, giving the third resonance structure. Okay, so it becomes now double bond here, H and E, and of course there will be a positive charge here. So you get 3 resonance structures. Intermediate is stabilized by this resonance. What about when attack is at C3? If electrophile is attacking here, positive charge will appear here, isn't it? So what do you get? What do you get? Attack is here, so the hydrogen is shown and electrophile is shown, positive charge here, and now what? Only possibility is that this lone pair can shift here, giving the next resonance structure, which will be like this, double bond here. Okay, and there will be positive charge over here, and no more resonance. So, when attack is at C2, there are 3 resonance structures. When attack is at C3, there are only 2. So, which is more resonance stabilized? This intermediate is more resonance stabilized. So, attack is preferred at C2. Okay, so that's how we explain the orientation in Furan. Now we'll take examples for electrophilic substitution reactions. A few examples. Okay. Yes, let's take a few reactions. Okay. Remember, substitution is preferred at C2. First of all, nitration. For nitration, we are not using nitrating mixture because that may lead to kind of polymerization. So we use a special reagent, that is acetyl nitrate. Okay, NO2 will appear here. You get the product. At second position, NO2 is substituted. What's the name? This is 2-nitrofuran. Then sulfonation. For sulfonation, we are not using fuming sulfuric acid, but SO3, which is the essential electrophile for sulfonation, which is used in pyridine. So you need a controlled condition for this electrophilic substitution of furan. Okay, because it may go to some other side reactions. So you get the product. Position 2 is sulfonated. You get SO3H. What about the name? This is Furan -2 sulfonic acid. Next is chlorination. You can simply chlorinate using the chlorine itself at low temperature of -40 degrees Celsius. But interestingly, you get mixture of product. I mean, there is mono as well as dichlorination taking place. So this is the monochloro, that is 2-chlorofuran is obtained, plus you get further chlorination at the next equivalent position. Generally, substitution takes place one at a time. I mean, mono substitution takes place. But here, it is found that further chlorination takes place. This position, this is also position 2 with respect to this oxygen. So you get dichloro. Then it is 2,5-dichlorofuran. Coming to bromination. Here, see a question. How do you get... See, if you do bromination also, you get this mixture. So how to get mono-halo derivative? The idea is, you have to take, in that case, not furan, you take this compound. Okay? What is this? This is furoic acid. So one position is blocked. Now you brominate it. You know what happens? Bromine will go to this position because this is blocked. So you get this 5-bromo furoic acid. Okay? Now what you do? You need only bromine. You need mono-bromo, 2-bromo furan. So what you do is you can heat it so that it will lose carbon dioxide and get 2-bromo furan. Coming to another reaction, this one is alkylation, just like Friedel-Crafts alkylation, but the catalyst is different here, SnCl4, not AlCl3. Anyway, it is Friedel-Crafts kind of alkylation. So alkylation takes place at the position 2. You get R here. This is what? This is 2-alkyl furan. So these are various examples for electrophilic substitution reactions of furan. Now I'll take some other interesting reactions of furan also. What are the remaining reactions? Look, Next is reduction, hydrogenation, addition of hydrogen in presence of palladium or Raney nickel. On reduction, adding hydrogen in presence of catalyst like palladium, what do you get? Simple. 2 hydrogen will be added, both will be broken, right? And what you get? You get saturated kind of product. This is known as tetrahydrofuran, THF, abbreviated as THF. It's a very important commercial organic solvent used for many purposes. Tetrahydrofuran. Because 4 hydrogen is added and it becomes saturated. Then oxidation. What about oxidation? See, simply in air, which contains oxygen, furan get oxidated, undergo oxidation, and the product obtained is interesting. What you get is a peroxide. O2 get inserted into this molecule, and what happens is O2 is attaching at these carbons, forming a product like this. So this is furan. Position will be 2,5 peroxide, isn't it? This is 2, this is 5. So we call it furan 2,5 peroxide. And this is highly unstable. It generally undergo polymerization products. Coming to next one, these are the reaction. What is that? See, in pericyclic reaction, in 6th sum you will learn about this reaction. That is a class of organic reactions called pericyclic reaction, in which one of the reaction is this kind of cycloaddition. Cycloaddition means 2 unsaturated system undergo ring closure. This is a 4 pi system. You understand? There are 4 pi electrons. This is a 2 pi system. So what happens? This undergo a ring closure, forming a 6-membered ring, right? 6-membered ring, and there will be a double bond here. You get cyclohexene. This reaction is known as Diels-Alder reaction. It is a 4+2 cycloaddition reaction. Okay. Now furan is similar to this. This is what? This is butadiene, butavantridiene. Furan has similar kind of moiety, structural unit, so it can add to a double bond. Technically in pericyclic reaction or cycloaddition reaction, this substrate is known as diene. This is called dienophile. You will learn in detail about this later. So this kind of reaction, if furan undergo, what kind of product you get? So we can write it now like this. Look here. This is furan. So it is a 4 pi system added to, let us take this compound, that is, tell me what is this compound? CH is here, double bond. So what is this? This is actually malic anhydride. You know that? Malic acid, CH dicarboxylic, and we have discussed that in the other module. So malic anhydride. So adding this system to this double bond, what you get first? It become like this. These two become a 6-membered ring, and the rest will be like this. Okay, you get this one, and of course this oxygen is there in the middle. So this is what you get. This you get a kind of this kind of adduct. This, when treated with HBr, undergo a kind of dehydration, and this become fully saturated, because you know there is a hydrogen here, one is here, so it can lose water easily, and the final product is this one. Can you say what is this final product? Can you name it? Let me draw. Can you name what is this product? What is it? This is phthalic anhydride. You get phthalic anhydride. And finally, we have next one is reaction with organometallic compound. Furan can form interesting organometallic products which is useful in synthesis. See, if furan is treated with, for example, this one, C4H9Li. What is this? This is N-butyl lithium, which is an important organometallic compound used in synthesis. This is straight chain butyl group, N-butyl lithium. This can react and get lithium gets substituted over here. So you get actually what you get is lithium gets substituted here. So this is Furan 2 lithium or 2 Furani lithium, you can call it. And this is now very reactive, just like Grignard reagent. You can introduce important functional groups at this position by substituting lithium. This is highly polar, reactive. So what you do is, if you treat with carbon dioxide and followed by acid, you might have learned this reaction, similar reaction in Grignard synthesis. So what you get? You get the product as, here this will become COOH. So what is the product now? What is the product now? This is furoic acid. So using such organometallic compounds, we can prepare organometallic compounds incorporating furan and produce various derivatives. Okay, so this organometallic compound is important in synthesis of various compounds. Finally, you can convert this furan into other heterocyclics like the nitrogen analog, that is pyrrole, or sulfur analog like thiophene, using respective reagents. If you treat with ammonia at a temperature of 450 degrees Celsius and in presence of Al2O3, this oxygen get replaced by nitrogen. What is this product? This is pyrrole. So furan into pyrrole using this reagent. The next one, using the sulfur compound, that is phosphorus sulfite, and if you heat it, oxygen is replaced by sulfur. What is this product? This is thiophene. So it's a versatile chemistry of furan is discussed here. Go through the reactions. We have actually one more compound, that is pyridine, to discuss in detail, and a brief account of the third one, that is indole, in the next video. Thank you.